more fun with circles. We're looking at section 10.3, which is dealing with chords. If you remember from the first section, a chord is a segment whose endpoints are on the circle. So I have two chords drawn here, chord AB and chord CD. You might remember CD is a special chord because it is also a diameter, but it is a chord. Both have their endpoints on the circle. Now we're going to mix that with what we did, section 2, about arcs. If you look at chord AB, it creates two arcs, a minor and a major arc. Arc AB is our minor arc, and arc AFB is our major arc. Okay, now if you look at that, we can't tell the measure of the arc by our chord, because remember our arc was created, get another pen, arc was created by the angle, the central angle that would make it. So we would have to know the angle to get the measure of the arc. But we are going to look at some relationships between the chord and the arc that it creates. Okay, we'll look at that in a minute. Chord CD creates two arcs as well. They are both semicircles. So we would say arc CD. If they wanted to have you look at a certain side of the circle, they would go ahead and put another point in there, and we would also could call it arc CED. But again, they both are semicircles, but the center one might tell you which direction to look at. All right, welcome back. Let's look at theorem 10.3, the first one from this section. It says, in the same circle or in congruent circles, two minor arcs are congruent if and only if, remember that, their corresponding chords are congruent. So that means that this is a statement and its converse put together. It's our biconditional statement. And what it says is, these are the two cases. This is a circle where you have two chords, and here we have two congruent circles. Notice they have the same radius. The radii are congruent, so that means the circles are congruent. All right, but what this is telling us is, if I know chord AB is congruent to chord CD, and they're on the same circle, then I know that arc AB must also be congruent to arc CD. That's what my statement says. Vice versa, if I know arc AB is congruent to arc CD, let's do this. If I know my arcs are congruent, then I could say that segment AB is congruent to segment CD. That's what my theorem is saying. Now the second case happens to be if we have two congruent circles and we know the arc AB is congruent to arc CD here, but the radii are the same, then I know that arc AB must be congruent to arc CD. All right, same thing. So let's look at how we're going to use that to solve a problem. Hang in there. Okay, welcome back. Here we have our example. Look at our circle here. We have two chords. Now notice they don't mark them congruent, but they do tell us they each have a length of 8. So we're supposed to know, okay, we've got two congruent chords here. Now according to our theorem, it says if my chords are congruent, then my arcs that they create are congruent. So we're going to answer these questions. Now we'll do them separate because we might get different answers. We'll do one first. So as if the measure of arc AB is 110 degrees, can we find the measure of BC? I forgot my little M there. There we go. All right, so we know AB is 110 degrees. According to our theorem, since my chords are congruent, then BC must equal the same thing, 110 degrees, okay? And that one's kind of straightforward, but let's look at this one. This is a little more interesting. This time they say if my measure of AC is 150. Now AC is the distance over here. It doesn't really have anything to do with our chords, okay? So let's put that together. We say this is 150 degrees, this arc measure. Can we find the measure of arc AB this time? Okay, so you got to think this one through. We know that the measure of AB must equal the measure of BC because my chords are congruent. But what they're giving me is the measure out here. So you have to start with, I know that the whole circle has a measure of 360 degrees. If I subtract that 150, that's going to give me what I have left over from to ABC, right? So let's start there. We're going to find the measure of AB. Let's skip that part to the end. We'll just start with what we find, the measure of ABC. Okay, so we can find this measure because we know that the whole circle, 360 minus AC here, 150, means that the measure of arc ABC is 210 degrees. Okay, so then the last part is, since we know these two arcs are congruent, I'm just going to divide that by 2 to find the measure of AB is going to be 210 divided by 2, or 105 degrees. Okay, see how that works? We're going to have a few like that. They might not be directly asking you the arc to the chord. You might have to work yourself around the whole circle. Okay, so watch out for those. Okay, we're back. We're going to explore a little bit with our chords on a circle. Now this time I tried really hard to get a good circle. See if this will work. Okay, so let's start with a chord. And I want to try to find the perpendicular bisector. Now again, this part I'm estimating, so hopefully you can get this pretty good. That looks pretty close. Alright, there's one. Let's try another color. Maybe kind of a big one. Let's see what happens this way. So again, estimate. Try to get it perpendicular, which is possible. My board likes to move a little bit. Okay, that's pretty close. Let's try one more, see if we can find something in common here. Let's do a straight line. Okay, perpendicular bisector. Okay, that's not too bad. All right, so if you look at what we've explored, notice that each of our lines, each of our perpendicular bisectors hits right in the middle. They say all hit each other, but it should be right in the center. I want you to try that. Try a few of them on your own and see what happens. Anytime we have a line, a chord, that cuts another chord in half, it's going to wind up being a diameter. Okay? Each one of these did the same thing. I guess I need to add some more lines there. Okay? So each time you have a perpendicular bisector of a chord in a circle, it will wind up being a diameter. Alright, and that's going to lead us to our next theorems. So hold on a minute. Okay, we're back. From our exploration, we have two theorems that come from it. So let's look at these. The first one says, Theorem 10.4, if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So I drew the if part of our statement. So we have a chord that cuts the other chord in half and is perpendicular. So our theorem says we know just by those two facts that it has to be a diameter. So some of your questions are going to ask you that. Can you prove this chord is a diameter? So this is what you're looking for. Is it a perpendicular bisector? Not is it one or the other. It needs to be both, right? All right, 10.5 then says, this is almost the converse, but it adds a little bit extra. If a diameter of a circle, so we're starting with our diameter, is perpendicular to a chord, then we know that the diameter bisects the chord and its arc, okay? So it adds the arc in there this time. So this time we start with a diameter. We know it's perpendicular to a chord, so that means by this theorem, the two sides there cuts it in half, but also the arc is cut in half, So we're also going to be able to find lengths of arcs, lengths of chords there. If we know that it's a diameter, we know that this would be true. All right, let's look at this example. We have one picture, but 4 questions we're going to answer about it. All right, so what they give us is circle A. We have a diameter BD, and we see that that diameter is perpendicular to our chord EC. So they're gonna ask us, how do we find the measure of chord CD? Measure of chord CD. All right, and so we know that since it is a diameter and is perpendicular to that chord by our last theorem, it cuts chord CE in half, and it cuts our arc CE in half. So they're going to ask us, how do we find from C to D? We know they are congruent, so that means that we can set our two expressions equal. That 9x equals 80 minus x. All right, so we're going to go ahead and solve for x, add x to both sides. We wind up with 10x equals 80, and x then is 8. So I need to plug that back in here. For CD, we know the measure of CD then is equal to 72 degrees. I should have put that a little bit further over there. Okay, 72 degrees. Now we're going to use our theorem. We know that it cut these two arcs in half, so we know DE must also equal 72 degrees using our theorem. All right, then they ask us, well, what about arc CE? Now this is using the theorem we talked about in section 2. We said if we have two adjacent arcs, we can find the measure of the whole arc by adding the two together. So we wind up with 144 degrees for CE. All right, let's look at the last one here, number 4. We're looking for the arc CBE. That's going the other way around. We just found CE on number 3, and we know that a whole circle is 360 degrees. So we can find the measure of arc CBE by doing 360 minus our 144 equal 216 degrees. All right, let's look at one more thing. All right, take a look at your first question. You're gonna write down the question and the answer for me at the end of the video to get credit for watching it. Question 1, what do we know if one chord is the perpendicular bisector of another chord? So think about it. We just talked about it. What do we know if one chord is the perpendicular bisector of another chord? All right, we talked earlier that we could tell two chords are congruent if we know that their arcs are congruent. But there's one more way that we can tell that two chords are congruent. It so happens that if we draw a radius from the center, well, it's not a radius. All right, we're looking now at congruent chords. We talked earlier about one way to tell chords are congruent is if their arcs are congruent, if they're in the same circle or two congruent circles. But there's another way we can tell that chords are congruent. We're going to find the distance that the chord is from the center point. Now, if you remember, when we find the distance from a point to a line, it's always going to be the perpendicular distance. So we're going to draw a line from our point here. Hopefully it's perpendicular. Okay. And do the same thing here. Okay. Now, if you find the distance of your chord to the center and it happens to be congruent, then we can tell that our chords CD is congruent to chord AB. And that's going to be our next theorem. Let's read theorem 10.6. It says, in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. So this is what we looked at just a second ago. But again, we're looking at two chords in the same circle or two chords in congruent circles. So we're going to look at it both ways, but also we're going to look at it from both directions because our if and only if tells us it's biconditional, so it goes both directions. in the same circle or in congruent circles, it says two chords are congruent if and only if they are equidistant from the center. So on this side, we show the distance from chord CD, chord AB to the center point is congruent. So from here, we know that we can state that chord AB must be congruent to chord CD. One thing to point out is that distance must be perpendicular. If they don't show the perpendicular sign there, we don't know that it is the actual distance. So you have to be careful of that. Look for your perpendicular. All right. Now going the other direction, then it is also true that if our chords are equidistant from the center, and I didn't mark that. If my chords are equidistant from the center, then they must be congruent, and I just did it completely backwards. Now let's look at the other case of our theorem. We're talking about two congruent circles. Notice their radii are marked congruent. And this time I'm starting with a step back one step. And I said, let's say arc xy is congruent to arc st. We know from one of our earlier theorems that that means the chords are congruent because their arc measures are congruent and the circles are congruent. So we have chord xy, we know, is now congruent to chord st. Now from this theorem, we know that if our chords are congruent, then the distance from the chord to the center must also be congruent. Notice the distance must, again, be perpendicular. So from this theorem, we know if xy is congruent to st, then the distance from xy, we can use 1. No, we need 3. The distance from xy is going to be congruent to the distance from st to the center. Now we're going to do an example, kind of putting all this together and see how we can solve for our sides. All right, here's question number 2. Write these down for me. Name 2 ways to tell if 2 chords in the same circle are congruent. We talked about 2 different ways. So 2 ways to tell 2 chords in the same circle are congruent. Let's look at our last example. We have circle C. We have 2 chords and we show their distance from the center. And we're getting all our information though from up here. I didn't mark anything on the picture, but they did tell us that ST is 32. So from here to here is 32. We're going to mark it kind of this way. Okay. And CU is equal to CV, which equals 12. So that does give us now some information. We know this is 12, and we know this was also 12. All right. So they're going to ask us to find QR. QR is the distance of this chord. We're given above that the 2 distance, UC and CV, are congruent. So that means our 2 chords are congruent, and QR has to be 32. There we go. Now QU is the distance halfway between Q and R. Now we know it's halfway because this is part of a diameter, right? We're going through the center, and we learned earlier that a diameter, when it cuts our chord perpendicular, then we know it's going to cut it in half. So we actually know that these 2 sections are congruent as well. That makes QU half of 32, or 16. All right? And the last one is kind of the fun one. The last thing they ask us is, what is the radius of circle C? So when you look on here, you might say, I don't even see a radius. These are part of a radius, but they're not the whole thing. But if we draw a circle, or draw a line from our center to any point on the circle, we have a radius. Let's go ahead and draw from C to R. Notice that we now have a nice little right triangle. So we can find, we'll use R for our radius. We can find R because now we know the length of the distance from the chord to the center, and we know, we just found out that QU and UR are equal to 16. So we're going to use our Pythagorean theorem. We've got 12 squared. UR and QU were 16. Let's write a 6 this time. 16 squared is equal to my radius R squared. Let's go ahead and remember we square them first. 12 squared is 144. 16 squared is 256. is going to equal our radius squared. When we add these together, we get 144 plus 256 is going to add up to 400. They give us a nice number this time. And we find r squared. We take the square root of both sides so that r equals 20. We actually can find the radius of our circle when we know the distance and the length, half of the chord there. All right, good job. Okay, that finishes up section 3 of chapter 10 on chords. Remember, you can't forget about them. They will come back, and we mix them up with our angles. We're going to go back to angles tomorrow in section 4. And hopefully you guys are doing good with the circles so far. Let me know if we're having any problems. So we're going to finish out with our joke of the day. Don't forget to answer the 2 questions and put the joke down so you get credit for watching the video and turn that into me. All right, here's our joke today. Did you know parallel lines have so much in common? It's a shame they'll never meet.